Welcome to another video for Stat 420. In this video, we're going to now be talking about confidence intervals and hypothesis tests for beta naught and beta 1. So as a quick review, let's briefly talk again about what we mean by doing inference, because we're now doing inference. So I'm going to draw kind of a box here. So I'm going to draw, let me get my marker the right size. So we talked about this idea that there's this box over here called the truth. This box has parameters in it. This box includes distributions that we don't typically know in real life. But if we happen to know this box, then we could calculate the probability of different observed data of different samples happening. So I'll also say statistics here. Right, so when we're talking about this process of here's some parameters, here's some distribution, what is likely to happen if I take a sample? That is called probability. It's also going to be related to simulation as well. So I can simulate from a particular population. However, when we're doing statistics, we're typically down here. We're typically doing inference, where we're starting with our sample results, and then we're trying to ask what could be the truth, what could be the parameters, what could be the distribution that this sample came from. So we talk about a confidence interval or a hypothesis test. We're starting with our sample statistics, and then we're saying, with the confidence interval specifically, let's estimate where the parameter could reasonably be. So if we want to make a 95% confidence interval for a parameter like beta, beta naught, or beta 1, we're going to start with our sample statistic, and then we're going to stretch a certain distance away from it, and we're going to decide that distance based on how confident we want to be and some other information about our sample results. When we do a hypothesis test, what we say is, here's a candidate parameter. How plausible is that? So given the sample that we have, could this particular value plausibly be the parameter? And we basically assume that parameter is true for a second. So basically we kind of simulate and say, okay, well, let's assume that's true. Let's talk about the probability of getting this particular result if that parameter is true. And then we can kind of judge the plausibility of that. We kind of look at the situation and say, is this probable or improbable? And if it's improbable, then we say, well, then this probably isn't the parameter. The parameter is probably something else. Okay, so we're going to focus first on confidence intervals. So the way that I would think about it is if the distribution of our sample statistic is normally distributed, which is the case for beta hat naught and beta hat 1, then there is just a parameter somewhere here, and most of the possible sample statistics I could see are going to be clustered around that parameter. So if I want to say that I want to be 95% confident that my confidence interval includes the true parameter, then I need to figure out how far away from the parameter do I have to go before I'm covering 95% of the possibilities. And that distance from the parameter is called the margin of error. So ME right here, I need to get a smaller pen. So ME stands for margin of error. Okay? And so if I know that stretching out a margin of error, let's just say 5, if I stretch out 5 units, and let me move myself again here, if I stretch out 5 units from the parameter, that range will now include 95% of the possible sample statistics, then that's how wide my 95% confidence interval needs to be. So when we make a confidence interval, we're typically starting from our sample statistic. So if our sample statistic is our best estimate, or sometimes we call it a point estimate. So in this case, beta hat naught or beta hat 1 would be our point estimate. And then we would stretch out the margin of error in either direction from our point estimate and say that we should be C% confident that this interval around my point estimate should reach the parameter one side or the other. So another kind of picture that we could use here is, let me move my myself again. So we have this graph up here at the top, and we have kind of our data, we have a sample statistic, and then I have an interval around my sample statistic. So if this interval is stretched out the appropriate margin of error, let's say for a 95% confidence interval, then 95% of the time, my sample statistic is going to be in this range such that the margin of error is enough to reach it. So if my interval is the size of the margin of error from on each side, I should say, then 95% of the time, my sample statistic is close enough to reach it. And about 5% of the time, I'm going to be in that 5% of the distribution where that isn't enough, right? So that's why we call it a 95% confidence interval, is because 5% of the time we could be far enough away by random chance that that's just not enough, but 95% of the time we will be. So the construction of a confidence interval, like how do we calculate this margin of error? So it's going to be the standard error of our sample statistic times the critical value associated with that amount of confidence that we want, as well as the degrees of freedom that we have in case of a t-distribution. So assuming that we're working with the standard error, that our sample statistics or that our standardized values follow a t-distribution, then I'm going to start with my sample statistic, and then I'm going to plus minus that t-value times my standard error. So if we do that, and we want to say like a 95% confidence interval, then t is probably going to be some value just a little bit more than 1.96. So 1.96 would be the case for a normal distribution. For a t-distribution, it's going to be a little bit more. The smaller the degrees of freedom, the more different it's going to be. The larger the degrees of freedom, the closer it's going to be to the standard normal values. If I want to be a more confident, so let's say I want a 99% confidence interval, I would need a bigger margin of error. So instead of just stretching out about 1.96 standard errors, I would need to stretch out, 2, 2.1, 2.2. I need to stretch out farther to have more confidence, right? Because if I want to take the chance that my sample statistic could be even farther than that, then the distance needs to be longer. All right, so let's do an example. So we're obviously going to be using R really to do this kind of stuff, but I think it's still helpful to kind of construct it by hand at least once and think about what the parts are. So let's say that we constructed a linear model to try to predict the stopping distance of different cars based on the speed at the time the brakes were initiated. We found the least squares estimate for beta hat 1 and also calculated the standard error for beta hat 1. Let's construct a 95% confidence interval for beta hat 1. So again, we know that our interval should be beta hat 1 plus minus our t-value times the standard error for beta hat 1. So then, we have this information provided, so I'm just going to plug it in. So my beta hat 1 value is 3.93. So this is my best estimate right now for beta 1. But because it's a sample statistic, I'm pretty sure there's going to be at least a little bit of error here. So that's why I'm going to build a confidence interval, is I'm going to kind of build an interval that I'm confident concludes the true parameter, because my singular point estimate probably has some error, and so I'd rather produce an interval than just a point estimate in this particular case. The 3.93 plus or minus the t-value associated with 48 degrees of freedom and 95% confidence is going to be 2.010635. And we could use R, for example, to calculate different t-values for different confidence levels, different degrees of freedom. And then we're going to multiply this by the standard error, which is going to be 0.4155128. And so this is going to give me a lower bound and an upper bound. So it's going to be 3.93 plus 2.010635 times 0.4155128. And my upper bound is going to be 4.765. I'll round it a little bit. My lower bound is going to be 3.93 minus and I get 3.095 if I round. Okay, so notice that our sample statistic should be centered in this interval, right? Because I centered it around 3.93. And this distance, by the way, 3.93 minus, say, this value, or 3.93 minus 3.095 would be my margin of error. So the distance from sample statistic to one end of my interval is called the margin of error. So then my interval itself should be 2 margin of errors wide. And so I'm 95% confident that the true the true slope value in this case, so beta 1, should be between these two values. Okay, let's also briefly talk about a hypothesis test. So similar notion, we're still doing inference. This time we're just judging the plausibility of a particular candidate parameter. I'm going to go right. I'm going to go up here. That's a good place for me to go. Okay. So again, we can represent, or really what we're doing is we're saying, let's assume this parameter, or this value is the parameter. Let's center a distribution around this candidate parameter. So let's say let's do the intercept here. It's centered around this beta 0, 0, this beta not 0 value. And so this is I'm going to call it a candidate distribution. For beta hat naught. I don't know if it really is, but let's just say it is and see what happens. So then I'm going to find the test statistic related to my particular beta hat naught, and I'm going to see how plausible it is. I'm going to see like how likely I am to get a value like I did. So let's say that my particular beta hat naught is like way out here. Okay? Well, that's pretty far. So that means that my test statistic is going to be really high. It's several standard errors below this candidate parameter. Well, then I can calculate a p-value. I can calculate the probability. I can calculate how often I would get a sample statistic this far or farther from this parameter if it was true. And if it's really, really small, then that gives me some doubt about this really being the parameter. It doesn't mean it's not the parameter, but it definitely questions whether or not it's the parameter. It makes me think that maybe the parameter is something else. So again, the null and alternative hypothesis that we're going to make. Let's start with let's start down here with the intercept. So if we're working with the intercept, then the null hypothesis is that the y-intercept for the regression line relating x and y equals 0, and or whatever value I want to plug in. So I guess this is a statement that we commonly do is does the intercept equal 0, but I could do a hypothesis test for any value I want. And then the alternative would be that the y-intercept for the true regression line is not equal to 0, or not equal to that value that I'm judging. If I'm doing a hypothesis test with the slope, then I'm making a statement about whether or not there's really a linear relationship between x and y. So the null hypothesis would be saying that there is no relationship, that there is no kind of line that the relationship between x and y does not actually depend on x, that y is independent of x. And the alternative here would be that there is some kind of linear relationship. So let's go ahead and do an example with beta hat 1, and let's do a hypothesis test where we're going to judge it in relation to 3 being the possible parameter for beta 1. So let's say that let's give the context that we have car manufacturer A says that for every 1 mile per hour of speed, the average stopping distance increases by 3 feet. Well, we have a sample from car manufacturer B of a similar model, and we're curious whether these two manufacturers' cars might follow the same relationship between stopping distance and speed. So let's judge the plausibility of 3 as a possible parameter for car manufacturer B as well. So in this case, I'm going to calculate a t-value that's going to be based on this difference between my beta hat 1 minus this candidate beta 1. And then I'm going to divide that by the standard error of beta hat 1. So this is going to be 3.9324, I'll just stop there, minus 3 divided by 0.4155, and then again I'll stop there. And so I'm going to get 0.9234 in the numerator divided by, 9324 divided by 0.4155. And I get 2.244 for my t-value here. And so again, I could use, say, R or somewhere else to turn this into a p-value. So basically what we're saying is, oh, that was a terrible normal distribution. So if this is really the parameter at 3, and I'm up here at about 3.93, right, I can find the probability of getting a test statistic that is this far or farther away from 3. And this is going to give me a p-value, and when I did this in R earlier, I got a p-value of about 2.9%. So basically, this right here and this right here add up to about 2.9%. So then I can make a statement from that. If you might remember, if we had a significance level, like say 0.05 or 0.01, I can just judge if this is lower than that, kind of that cutoff point. But in general, I would still look at this, even without a significance level, we can still kind of look at this and say, this is pretty low. It's definitely not impossible, but it is kind of improbable. Like it's pretty low. So that gives us some evidence, we might even say fairly strong evidence against this null hypothesis that it's really 3. It's not super strong evidence, but it's definitely enough to make us really question and think that it's probably higher, like the true average for car manufacturer B is probably higher. But we could use a significance level and make a formal decision of reject or fail to reject depending on whether or not we're higher or lower than that cutoff.